As the leading cause of death, coronary artery disease claims the lives of millions of people in the world every year. Among people with this disease, the amount of calcium deposited in the coronary arteries is highly predictive of heart attacks that lead to lethality. I built statistical models that predict the presence of coronary calcium using data gathered from several male patients within the age range of 50 to 65 with and without high levels of coronary calcium. In these models, I used three classes of variables: clinical variables, DNA markers, and the levels of 100 transcripts that are expressed from 46 genes previously associated with coronary calcium in the literature. The models I have developed are composed of several decision trees. In each decision tree, several variables collectively decide the outcome. Each tree branch is split into two branches based on a variable's threshold. Using 2/3 of the data, these thresholds are optimized by creating the optimal separation between healthy and diseased patients. With the remaining 1/3 of the data, model predictions are generated using a democratic voting scheme. If more trees vote for the healthy state, a patient is predicted to be disease-free. For such models to be effective for personalized medicine efforts in saving lives, their accuracy is the key. When I only used clinical variables, the accuracy was 79%. With the addition of DNA markers, the accuracy went up to 84%. When I also added the gene expression levels, the model performance peaked at 95% accuracy. My goal was to find the best predictors of coronary calcium. By perturbing the gene expression levels and identifying the effects of these perturbations on the model accuracy, I found the predictive power of each gene. As I plotted these values for all cases including extreme coronary calcium levels on the y-axis and without those cases on the x-axis, I found that 11 transcripts that are expressed from one gene named DDR1 were the best predictors of coronary calcium. DDR1 is a recently emerged marker that's known to activate multiple biological pathways that are associated with the early onset as well as the late progression of cardiovascular disease. It also has a favorable biochemical structure as a therapeutic target. My findings suggest that by inhibiting the activity of DDR1, we can prevent advanced levels of coronary calcium. This would help us get closer to a major aim in the field of cardiovascular disease, that is, moving away from clogged arteries and moving towards healthy hearts.